somebody's response has been recorded.
I did.
Somebody's response has been recorded.
Yep. Fine.
Yeah. So he passes, the rest of you are gone.
What channel?
What channel did you use? The magic channel?
I just press channel and then press 2.
Yeah, channel and press 2. I'm not press. So he's giving you the answer. Okay. Okay, let's see. I got 2 now. I got 2 responses. So let me see.
I just press channel and then you so when I press the channel, it was a green red switching over.
And what channel is it showing?
41.
41. Channel is 41. We are CS people. We're going to figure this out. 4. I have 4 people answering this question.
What is one guy?
It is what?
What light is supposed to flash after you select your answer?
No. We are not telling you what the right answer is. Right? No, if you are on channel 41, it should work.
I know, but should it flash green once you do something?
I don't know.
No, it just flickers on green and red, and when you press the option, it ends with a red. So.
Does it say anything?
Okay, 6. You guys are going to figure this out. We're going to train you.
How do you know? How do you know if yours was taken? Like what it says?
Because there was only one vote that got
7.
and I was the only one who did it.
Okay, so by the time the class is over, at least you would have done this. I didn't know why I came all the way from Los Angeles for this, but you know. Okay, figure this out still. Yeah, is it 44? Some people are saying 44, some are saying 41, and I have gotten up until 12 or 13 now. It's 44 everybody.
How do you change channel? Channel or channel?
Should I press something?
Alright, you work on 44.
What?
So press channel, then 4 delegate channel.
Oh, cool.
Yeah, and then you press channel.
Do you have one on?
Yeah, when you press the channel, make sure that it's off. So now when it's off channel,
Show your answer.
36, man.
When it goes through? What? Yeah, when
As
it
long as we don't go
shows you picked it.
at this pace for each other
I don't know
questions.
if you ever got it.
Alright.
Okay. Is there anybody else who hasn't clicked? 44, 45. Feel like this guy, what's that, good clerk or somewhere? Who does this? Times Square.
Yeah, it's 44.
Okay, so I'll just write this down. Today's channel is 44.
How about I propose another option, E, not enough time.
Well,
Yes. So not power E, not enough time.
I was told that you guys were given 20 extra minutes. And I only took 1 or 15 minutes to write the answers. So I assume you'll do it faster than that. Anyway, okay. Okay, fine. 51, I'm going to actually, is there anybody else who's having trouble operating one of these things? Okay, so I'm going to basically stop. I guess I assume everybody who wanted hold, okay? Okay, so we'll know the answer right now, one of these times. Oh, there. See, lots of people think it's reasonable. I guess I helped that I was clicking on the side. But, okay, that's that. So my exams are generally long. In fact, it's said to be only 1 hour 15 minutes. It was just that since I wasn't here, you guys wound up getting extra 20 minutes. You know, so it will be long. That's the usual thing. Okay, but generally, very few people found it excruciating. And why aren't enough people finding it easy, please? I don't know. Okay. How is the progress on? Okay, this one I need to open this again. Okay. Now let's do this fast. Okay. Because otherwise you'll just be doing this the whole class.
All pretty close.
39, 40, 41. So this also tells me how many people aren't showing up. So this is actually attendance. Okay, I'm going forward. We have 50 people, that's it in the class. Okay. So this is actually a quiz, we'll get extra points for doing this. Okay, 51, that one guy suddenly poker. Okay. Okay. Well, I'm going to stop. And let's hope that A is the answer. What? I think you guys are playing the game theory. Okay. The next one, so less than half done. So the entire weekend is still available. Actually, I should have put haven't started yet as a possibility, and then see how many people actually. Okay, next. Oh, okay. I need to start. I'm sorry. Yeah. Wow. The moment I started, it went to 31. So people are like dying here. Like, how? Hey, it increases now. It's 54. Okay. 55. They're producing people?
I think some people trickle in.
Okay. Okay, so the homework 3 is now available on the blackboard, and it is about geometries and Markov-Addition processes, and we set the deadline to be next Thursday, 11:59. Okay. I'll take the fact that most of you seem to still need time for project part 2 into account. I'll send you a mail about probably slightly extended deadline. But please don't just ruin the weekend by watching movies. Just do the project. That's the, I can just make this the only project for the whole course, and then you'll learn nothing. Okay. Actually, I just need to write it. Okay, now, real questions. These are MDP questions, okay? Think about it and answer. These things will actually count. It's probably, also it's kind of more fun. I'm assuming that all of you watched the MDP lectures, either showed up or watched, okay? It's the most fascinating topic, except for the next one and next one. But anyway, it certainly is the most fascinating topic. Okay. Okay. So, which of the following is not true about MDP models? So you are talking about what is not true.
What is this?
What?
What does that mean?
Which one?
Can you rephrase that?
This one.
Yeah.
They subsume the state search models. So state search is basically the A-star search that you have done. Remember, we did A-star search and then we went into MDP. One of the things that I want you to learn by today, end of today's class, hopefully, is in what way is MDP connected to A-star search. You sort of know this already to some extent, okay? But you'll learn a lot more today, especially part of the quiz itself, actually. But anyway, so basically, this question is, so MDP subsume state search models is the statement. So if you think that, in fact, you can write A-star search as a special case of MDP, then you will assume that's a true statement. If you don't think so, then you would not answer that question. Okay, let me see how many people answered. 41, 45. Yeah, so I have to come here to vote people. Okay. Okay. Stop this. Okay, they do allow stochastic actions, cannot be. Okay, I would like to play this game. when I do this, I would like people who pick the wrong answers or the minority answers. Minority doesn't necessarily mean wrong, okay, to explain why they picked it. I won't know who you are until I go back and check. But if somebody, that's the way, I may have mentioned this, that all, the Tolstoy quote, that all happy families are alike. They're all happy in the same way. Every unhappy family is unique in its own way, okay? And everybody who understands the right way anyway. The people who have trouble, figuring out something, they all have different reasons. So part of the reason for doing this quiz is not just to give you the right answer, but also to see why you might be thinking about the wrong answer, okay? So some people thought they thought this is the answer. That means they don't think MDPs allow for stochastic actions. Anybody who picked that would like to care to speak up? I understand it's a minority view, and normally there is this general feeling that if I'm in the minority, I must be wrong. Okay, it's not always true. Okay, but if you'd like to speak up as to why you thought so. Okay, so Markov-Ricci processes actually do allow stochastic actions. That's one of their advantages. So that can't be the false statement. They allow for generalized goals. Some people seem to have thought they allow for generalized goals. I mean that they don't allow for generalized goals. Yes.
Honestly, I thought all of them were true, so I kind of just went through the answers. I kind of think C is the one that's false now, but I guess I ended on B because in the timeline I kind of thought sub goals instead of generalized goals. So hit one sub.
So the thing about generalized goals basically is the reward function allows you to specify both goals of attainment as well as goals that you get, the rewards that you get for passing through the various states. So it actually turns out that it's a more general framework. Their more generalized goals can be allowed. It's an assembly language to some extent for all sorts of interesting goals to be compiled down into reward metrics. Okay, so this and these are actually true statements. And now this becomes more interesting. The third one, the subsume state search models. A whole bunch of you thought it's not true, right? That's why you picked that. So anybody who picked that, can they explain why they thought so? I'm not saying it's right or wrong. I just want to know. This whole point is not just clicking something. Actually, standing behind your answer. Yes, please.
I thought because you don't have, you could do you can search the whole, this model does allow for looking at the whole picture, so you don't have to search based on the state.
No. So first of all, the state search models as well as Markov-Ricci processes, they have the notion of state. Okay. So is there anybody else who has a different answer? I mean, I'll talk about that, but is there anybody else who had a different reason for thinking that to be the wrong statement? Or everybody more or less believed that, or the rest of them just clicked? Yes?
Well, it was just process of elimination.
What?
It was process of elimination for me.
Process of elimination, thank you. Okay. That's not I can't question that. Other than to say that you didn't eliminate the right things, but any other different answer? So state search is basically completely subsumed by Markov-Ricci processes. We talked about this in the lecture. If you actually watched the lecture, I kept on saying that in the beginning. In essence, you can do anything that A-star search does, using an MDP model. A-star search does not allow generalized goals and stochastic actions, whereas MDP allows both of those too. If you have deterministic actions, it's just a specialization of stochastic actions, where one probability is 1, all the other probabilities are 0. Right? And similarly, if you have goals of attainment, where basically you get all or nothing by just going to the goal state, that's fine. You just basically have reward is 0 in all the states, except for some terminal states where the reward is non-zero. Okay, so state search does subsume MDP. So that's actually a true statement. Again, in answering this, we are essentially reviewing MDP, right? Then finally, they allow for partially observable environments. A lot of you said that is actually the false statement. What? Yes. So that indeed, so MDP by itself does not allow partial observability. And that's why it can look at the state it is in. It's fully observable, but stochastic. These are two very different things. Okay? So if I'm tossing a coin, it's a stochastic action. When the coin falls on the table, I can still say whether or not it's heads or tails. So it's fully observable. If I am a blind man tossing a coin, then I'm using stochastic actions as well as basically partial observability. Because I can't see what state I am in. Okay? MDPs assume the state is known. And that state can be observed. And that's what makes life easy. Okay? As I mentioned in the lectures, PALM DPs essentially have to search in the space of belief states. Now, belief states is not too bad, you might think, because after all, we just did talk about if there are S number of states, there are 2 power S number of belief states, we said earlier. Right? Because, a belief state is nothing but a subset of states. However, that assumes that there is no difference between saying that I think I'm in state S1 or S2 or S3 with 0.333 probability each versus I'm in state S1, S2 or S3 and this is 0.7, this is 0.2, this is 0.1. Do you understand what I'm saying? If you have probabilities about how likely is it that you're in a certain state, then it's basically now suddenly you have infinite number of belief states. Not just exponential, but infinite number of belief states. Because you can take any set like this, right? And then come up with 3 positive numbers that add up to 1. There are infinite such combinations. So partially observable Markov addition processes basically search in the space of belief states, which are really discrete distributions over the states. The number of discrete distributions are infinite.
What did you call it? What was originally called found MDP?
PALM DP, partially observable Markov addition process. PO, partially observable MDP. They just call it PALM DP. Okay. Any questions on? Yeah.
Can we talk of steady states when we discuss about MDPs?
What do you mean steady state?
Maybe certain states which are more likely to occur?
No, that's basically, again, that's actually an interesting question. That's actually an interesting question, but I don't know whether you meant it that way or not, which is there, so some of you may have, so you heard about MDP, we are talking about MDP right now, right? I hope that many of you have heard about a thing called Markov chain. How many of you have heard about Markov chain? Right? What's the difference between Markov chain and Markov decision process?
MDP is a Markov chain.
Markov chain, you are a spectator. The chain evolves. So you can ask things like, is there a steady state to the chain? In a Markov decision process, you are not a spectator, you are a player. You change what you get to decide what action to do. Do you understand what I'm saying? In a Markov chain, how do you provide a Markov chain? You will say states, and you will say, if you are in this state with this probability, you will go to this state, this other probability, you will go to this state, and so on. Who picks which state you go to? Essentially, the nature picks. You don't have a choice on which transition you get to make. Whereas, in the context of MDPs, you have multiple actions you can do. Each action has a different set of transition functions. So, for example, I can pick an action which is very uncertain in its outcomes. It can put me in any of the 3 different states, or I can pick a costlier action which is way more certain about which state it will put me in. And it's my choice which action I pick. So this idea of the connection between Markov chains and Markov decision processes is a very, very nice one. And in the context of Markov decision process, in the context of Markov chain, you can ask what is the steady state distribution. Okay, now if you are the agent playing the MDP using a policy, outsiders think it's a Markov chain. They can compute the steady state distribution of it. you can argue that nature is playing a policy. It has an MDP. I didn't say he or she, I said it. And so that I won't get accused of over religiosity. And then basically it's going to base, it has picked a policy. According to the policy, the transitions will occur. But outsiders can essentially see that, an observer sees it as a Markov chain. The word that is different between Markov chain and DP is the D part. And if you're an agent and you don't have a D, that means you don't have a decision-making power. What kind of an agent are you? You're just a spectator. Calling yourself an agent is overkill. Yes?
So if you are an agent that tries to find a policy and you would employ MDP to figure out the best course of action, if I would be an adversarial agent, could I use Markov chain to know where you might end up?
That's a very, very good point. Yes. In fact, by the end of this class, if we actually get through this quiz, I will connect MDPs and game trees. And you can think, just to give away a little bit, you can think of MDPs as a game against nature. Do you see what I'm saying? So remember how we used to have, we had this, in a game trees, we had this situation, right? Max can do this, at which point Min can do one of these things. That's what we did, right? Now, instead of Min being a player, Min is a nature. Min is the nature. Okay, and previously, we basically said the Min will do the thing that is most damaging to you. One thing that's worthwhile understanding is nature doesn't care about you. It's indifferent. It's not out to get you, it's not out to help you. It's just indifferent, it's doing its thing. Okay, so if I happen to know this is 0.7, this is 0.2, this is 0.1, that means basically nature is playing a dice. And if it comes this phase, it will pick this outcome. If it comes this phase, it will pick this outcome. If it comes this phase, it will pick this outcome. If you do that, then you are actually solving MDPs using game tree search. We will get to that, and in fact that is a faster way of approximately solving Markov decision processes. This whole thing about value iteration and policy iteration we'll talk about in the beginning, that's like the bedrock, that's a way of exactly computing optimal policy and value. Most MDPs are too hard to actually compute optimal policy and optimal value. Instead, just like game trees, you would do depth limited search and backup. The only thing that's different is in the other case you did min-max backup. Here you do expect and max backup. Do you see what I'm saying? So that's the connection with the games. And in that sort of a scenario, in fact the question is, how did you figure out these numbers, 0.7, 0.2, 0.1? You must have watched nature previously. You did this action multiple times, you saw what nature was doing. And then you learned from that these must be the probabilities. And then you start using it in your inference process. Okay? Next. And compared to the state search, the reward function in MDP, this is too easy. But anyway, do it. Which of them is true? Come on, guys. This you should know. I mean, there are actually hard questions coming up. I'm told this is called active learning, where you actually try to answer before being told you are wrong, as against just being told you are wrong right away, before you even speak up. Okay, but this is good because you try to think. 55. I don't think we have any. 56. 57. Okay. I think I should stop before we cross the threshold. Okay, I'm stopping. I'm going forward. Well, somebody else can, but Okay, let's see. somebody who thought reward functions are a generalization of the heuristics, could they say why they thought so? I mean, you guys did do it, right? 23% of you thought so. Yes.
I guess one of the things.
By the way, thank you for speaking up when you are a minority. That's what life is all about. That's the only way you'll learn whether you're right or wrong. Okay, go ahead.
Just one of the things that struck me was just the whole, the fact that it's partially based off of the probability as well, and so it just seemed to me it was more of a generalization.
Okay, so here is a very interesting point to understand. In fact, this will be coming up next. Reward is computed or is it given as part of the problem? There are two different things, right? Is it part of the specification or is it something that you compute?
It's given.
It's given. That's an important distinction to have. Okay, the goal, the agent doesn't get to decide what its reward is unless it has access to trucks. Then it says, okay, today my reward is going to be 15 units. Take the truck and you'll get 15 units. Okay, but normally, you know, the reward is decided as part of the specification.
But is it so the same with the heuristic function? You can compute the distance, say, but the function is given to you.
No, you decide. I mean, so, no, the heuristics are not given to you. If they were given to you, then why did we spend all this time about different heuristic
You
functions?
can pick any heuristic you want.
Yes.
So you leave that.
Okay. But keep this in mind, by the way. And then somebody who thought reward is a generalization of the solution, would they like to say something? See, as I said, MVPs are a very, very interesting general model. The more intuitions you get about it, the better off you are. Just in real life, forget about this class. Okay? So it's good to have this discussion. So generalization of solution. Anybody who thought it was generalization of solution, care to explain why they thought so? Yes?
It's like you said the whole path matters, right?
What?
The whole path matters in MVP.
No, I'm only asking, is the reward function generalization of the solution? Reward function basically tells you for a given state, you get these many units of reward. Okay? Again, the way you're answering this question should also tell you in the back of your head, if most of these are like, you know, while wasting my time, that means you understood MVPs. Okay? If you're struggling, then you at least heard the lecture. If you're clicking, then you are gone. Okay, you should find another class. Okay?
So can you explain why A is the correct answer? If you did
Rewards, basically we did point out that reward function can be thought of as a generalization of goals. You know, if you have goals of attainment alone, then reward function would be zeros everywhere except for some terminal states where there is reward. If it is more generalized kinds of goals where the journey also matters, then you will provide like rewards for every state. So reward function, if you compare state search and MDP, you know, state search has goals. MDPs have rewards. Rewards are just generalization of goals. State search has actions, MDPs have actions. MDPs allow stochastic actions, normal state search allows just deterministic actions. There was a question, yes?
So what's the difference between a solution and a goal as with the solution?
Okay, that's a very good question. Solution in state search is the sequence of actions. Right? That's the solution of the problem. Goal is basically the state that sequence of actions should put you in. See, any sequence of actions is a potential solution. It's a real solution if after you execute it, you will be in the goal state. Okay, solutions for A star search are sequence of actions. What do you think? As I'm going forward, what is the solution for MDP?
But for MVPs then, could we say that we have little goals
What?
along the way of the path we're trying to find?
You
to get
could,
to
that way basically, all I'm saying is reward function is the analogy for goals. It's a more general notion of goals. And it turns out all sorts of crazy kinds of what you might consider goals can be compiled into reward functions. Yes?
If you use the example where you had the diagrams with the grids and the arrows, and you had the RS, all RS greater than 0. So then in a way the goal was never actually a terminal state. In my mind, the terminal states represented goals themselves, but you had the arrows.
So actually the interesting thing is there doesn't even have to be terminal states for mark coordination processes. The example we gave had terminal states. Okay, that means when you get to that state, no action can be done. But it turns out that you can have well-defined optimal policies for mark coordination processes, even if there are no terminal states. Do you understand what I'm saying? Again, the minimum I want you to understand is rewards are a more general way of expressing goals. Okay? So, what is the solution for mark coordination process? You asked, basically what is the solution? And I told you, solution for A star search is a sequence of actions. What's the solution for a mark coordination process? A policy. It's not a sequence, it's a policy. It's a state action mapping. And I went on and on in that lecture about why you need a policy as against a simple sequence of actions. Because simple sequence of actions means after I do this action, I know exactly what state I will be in. But things like man proposes, God disposes, all this stuff comes because you do an action expecting an outcome and some other outcome happens. And then you don't get to cry saying, it did happen, what do I do now? You should have figured it out and you should have done, if I do this expecting this to happen, so for example, you had a policy. I will start working on the project assuming that it will be due on Monday, but I'll keep some hope open in my mind that everybody will collude and say none of us got done with the project, in which case I get to see this movie in the weekend. So you figure this all out. And some of you are probably going to replan. That's also possible. Replanning can be optimal because maybe this movie that you have to see in the weekend, you should have bought the ticket on Wednesday. And if you only try to do it now, you won't get the ticket. Whereas if you plan, you keep the ticket and then you'll scalp it if you're not going to the movie. Again, this is the whole point about, you can have a sequence of actions, try to do just that, and if you fail, then quickly try to figure out what other action, if you find yourself in an unfamiliar state, try to figure out what action should you do there. That would be the notion of replanning. So you do series of state searches during the execution itself. Whereas planning means essentially figuring this out all up front. Okay? So you have figured out for each contingency, for each state you can find yourself in, you know what to do. That's what is figuring out the policy. Now, having said that, how many of you think that it is a wise policy to compute optimal policies? I'm using wise policy in English sense and compute optimal policies in a technical sense. How many of you have heard this saying by a great philosopher? Life is what happens when you are busy making plans. First of all, who is this great philosopher? Come on. John Lennon. John Lennon said, at least the last